Hello and welcome to podcast.init, the podcast about Python and the people who make it great. You can subscribe to our show on iTunes, Stitcher, TuneIn Radio, or add our RSS feed to your podcatcher of choice. You can also follow us on Twitter or Google+, and please give us feedback. You can leave a review on iTunes so that other people can find the show, send us a tweet or an email, leave us a message on Google+, or in our show notes, or you can join our discourse forum at discourse.pythonpodcast.com. I would like to thank everyone who has donated to the show. Your contributions help us make the show sustainable. For details on how to support the show, you can visit our site at pythonpodcast.com. Linode is sponsoring us this week. You can check them out at linode.com/podcastinit and get a $20 credit to try out their fast and reliable Linux virtual servers for your next project. I would also like to thank Hired, a job marketplace for developers and designers, for sponsoring this episode of podcast.init. Use the link hired.com/podcastinit and double your signing bonus to $4,000. We are recording today on January 18th, 2016, and your hosts as usual are Tobias Macy and Chris Patty. Today we are interviewing Aaron Meurer about SymPy. Aaron, could you please introduce yourself?
Hi, my name is Aaron Meurer. I am a research scientist at the University of South Carolina. I work with Anthony Skopatz, who was a previous guest on this show. I work at his lab, ERGS, and I'm presently working primarily on SymPy, which is what we're going to be talking about today.
So Aaron, how did you get introduced to Python?
Yeah, so back in my freshman year of college, so I originally was a computer science major, but our computer science courses were taught in Java, which I immediately didn't like. But there was a free course that was offered at my university about a language called Python, and I figured, it's good to have some language diversity, so I went and I immediately fell in love with it. So then I learned some more. I did some Project Euler problems, learned some more, and then that summer I learned about Google Summer of Code, which is a program that Google runs every summer where they pay college students to write code for open source projects. And through that I was able to discover SymPy, which is basically the perfect project for me because I'm a mathematician and I also love programming and I love Python. And so SymPy is a computer algebra system in Python. So that's like all three right there. And I did a project for that in Google Summer Code, and I've been working on it ever since. I got hooked.
Yeah, it's amusing how often I hear Project Euler come up as a intro to various programming languages for people wanting to learn something new. I think it's cropped up a couple of times on our show, and I've also heard it a few times on the Ruby Rogues show and various other places. So I've done a few of them myself as well, and they're definitely a great test bed for trying out new algorithms or new programming languages because the problem itself is decently constrained, so you don't have to worry about getting too deep in the weeds.
Yeah, although they are pretty hard problems.
Yeah.
There are certain languages that I would maybe be interested in learning, but I don't know if I'd want to jump in with Project Euler because they're pretty hard.
Certainly. I don't think I would want to use Haskell as my intro to Project Euler.
Or Bash.
Yeah, certainly.
So what is SymPy and what kinds of problems does it aim to solve?
Right, so as I said, SymPy is a computer algebra system, so something like Mathematica or Maple. What it means is that SymPy is doing mathematics symbolically. So unlike something like SciPy, where you have a bunch of mathematical functions and you pass in a number and you get out a number, with SymPy you actually are doing things symbolically like you would do in a math class or on a whiteboard. So for example, you can take symbolic derivatives, do symbolic integrals, you can solve functions and get a symbolic solution. So SymPy has a whole range of different modules for different kinds of mathematics, and all sorts of people use it for different things depending on what you're doing. I personally like to think of it just as a more advanced calculator. So a calculator, as you usually think of it, just as numerical things, like addition and subtraction of numbers. But a symbolic calculator lets you symbolically calculate things. So if you want to, solve a quadratic equation or a more complicated equation, get a symbolic solution.
Very cool.
And how did the SymPy project get started?
Yeah, so a guy named Andrei Chertek back in 2005 was a graduate student and a physics graduate student, and I guess he wanted to do some things that require a symbolic system. He's a theoretical physicist, so there's a lot of symbolic calculations that are involved in that, which I personally don't know much about because I'm not a physicist. But he also wanted to use something that was open source, and I guess he wasn't really happy with the open source solutions at the time, especially since I guess he also liked Python, and Python at that time didn't really have anything else. So he started working on it, and some other people used it, and they improved it, and it ended up growing into a full-featured computer algebra system over the years.
So how did you get started with the SymPy project?
Right, so back in 2009, I did a Google Summer Code project, as I mentioned earlier. I kind of discovered it, I think, just through looking through the Google Summer Code projects, looking at the Python projects that had to do with Mathematica. And so my project was to implement ODE solvers. So you would input a symbolic ordinary differential equation, and it would give you a symbolic solution. So, for example, you could enter something like derivative second derivative of f of x equals f of x, and it would spit out the solution to that, which is, or I guess, is that the one that I want? Yeah, I think that's a sine and cosine. It's been a while since I've actually done that math. I kind of got hooked on it on that point. The open source philosophy, I really agree with that philosophy, and just Python and math and the SymPy community is also a really great community to work with, and I found that it's a great way, working with open source is a great way to learn just about computer science and whatever the open source project happens to be working in.
Yeah, I can totally understand why you could, become fascinated by the project. I mean, when I first encountered it, I was kind of blown away. It's like this magical mathematical blackboard that, you can sketch out your equation and have it actually get solved and have the results displayed in a beautiful way. It's really kind of impressive.
Yeah, when you first see it, it's kind of like, wow, how does this work? And then you dig into it, and some of it, you see how it works, and you're like, oh yeah, okay, that makes sense. And there are some parts that actually, there's actually some deep mathematics going on there, and it takes a little bit of understanding to know what it's actually doing.
So are there any limits to the complexity of the equations SymPy can model and solve?
Oh, absolutely. It's extremely easy to make a symbolic expression that arbitrarily complex. There are a few problems here, theoretically even. There's something called zero equivalence testing, which is basically the problem of given some symbolic expression, you want to know, is it identically equal to zero or not? So, for example, say you have the expression sine squared of x plus cosine squared of x minus 1. We know that due to some trig identity, that expression is actually identically equal to 0 because sine squared plus cosine squared is 1, and then I subtracted the 1. And so there's a theorem called Richardson's theorem that says that as long as you have enough functions that you're dealing with, which is actually not very many functions, basically elementary functions, I think absolute value, and I think you have to include pi. As long as you have enough functions, that problem is intractable in that it's undecidable. So it's not NP complete, it's actually undecidable. It's physically impossible to solve the problem in generality, meaning there's no algorithm that can do it. That's not to say there aren't heuristical algorithms that can solve it for some problems. But what that means for SymPy is there's always going to be cases where it's not going to work. And a lot of the algorithms sort of do like some sort of pattern matching heuristics where if your input expression sort of looks like something that it knows how to solve, or if it can sort of manipulate it into something that it knows how to solve, then it can solve it. But in other cases, you can easily construct some other thing that doesn't work. So I would say, yes, the complexity is actually a big problem because you can make symbolic expressions that are sort of arbitrarily complex without making them particularly large. So it's not like you need to have some huge expression for it to crash. You can actually have some very small expression, and that'll be sufficiently difficult.
And how does SymPy compare to similar projects in other languages? I know you mentioned Mathematica and Maple. I don't know if there are any others that compare favorably or unfavorably to SymPy.
Right, so Mathematica and Maple are sort of the big proprietary computer algebra systems, and yeah, they're actually quite powerful. Mathematica, I would say, is sort of the gold standard as far as computer algebra systems. It's extremely capable. There's a lot of people working on it. But it also costs a lot of money to use. There are several open source computer algebra systems as well that compete with SymPy. For example, there's Maxima, there's Axiom. A lot of these are actually quite old in their roots. Some of them date back to the 70s. People were first starting to actually invent computer algebra.
Yeah, I was going to actually say, I know for a fact that I've seen references to Maxima going all the way back to McCarthy and Lisp 1.5 on the, DEC 10 and DEC PDP series computers in way back when in the olden days of prehistory.
Sure. Well, I mean, McCarthy's original Lisp paper shows how to use Lisp to construct symbolic expressions and then how to symbolically differentiate them. I'm not sure if that's actually the beginning of computer algebra, or if there's stuff before that. I don't know the history that well. But yeah, so as far as how it compares, some of these older systems they do have some algorithms which are more advanced than SymPy. But the thing about SymPy is that the things that it can do are actually quite broad. So there are some areas in SymPy where it's very advanced, and there's some areas where it's less advanced. I'd say that one of the main advantages of SymPy is that it is open source. So unlike Maple and Mathematica, you don't have to pay for it. It's written completely in Python, so that means that it makes it a lot easier for people to learn the language around the computer algebra system. Most other computer algebra systems sort of invent their own language. Like Maple has its Maple language. Mathematica's got Wolfram language. But even like Axiom and Maximum have their own little Lispy languages that they've invented, which means that if you want to actually do programmatic stuff, you have to learn this language. And so the idea behind SymPy is that we're not really language designers. We're mathematicians and physicists, and we'd rather do math than try to figure out what good language constructs are. So we just we use Python as our language. Python tends to be a pretty good language.
Yeah, I think knowing your strengths and avoiding the crevasses is an important maxim for good design, to be sure.
I mean, there are plenty of other advantages too. Like, SymPy is in the Python ecosystem, so it's easy to start with SymPy and end with some other library that in Python, like say Matplotlib or SciPy or something else that you want to do that SymPy doesn't necessarily do. And because Python is sort of acts as this has this huge scientific ecosystem, and it sort of acts as this glue language, it's really easy to integrate symbolic stuff with SymPy into other scientific workflows.
Very cool. And I can only imagine that things like Jupyter Notebook really sort of leverage that to its fullest, right? Like you use something like the Notebook, and you can sort of use SymPy along with other things in concert to sort of solve your problems in really efficient ways.
Yeah.
So how does SymPy render results using such beautiful mathematical symbols when the inputs are simple ASCII?
Yeah, so one of the features of SymPy that it's actually one of my favorite features is the printing system. So SymPy has several different ways of, once you have an expression, of actually displaying it to you, depending on what sorts of capabilities you have. If you are in the Jupyter Notebook, you can display the expressions using the Mathjax LaTeX renderer. So it's basically going to show you this really nice mathematical representation. But if you're using SymPy in a terminal, we have these pretty printers that use all these fancy Unicode symbols to basically print expressions in a way that is quite readable. There's actually, I don't know if everyone knows, but the Unicode has a lot of these symbols for drawing shapes and things like that, where we can use those to do things like actually draw the square root symbol on the screen, or draw an integral sign on the screen, and then you stack the different expressions on top of each other so that it's perfectly readable 2D expression.
That's kind of one of the aspects of SymPy that was totally amazing to me, is that I would sort of, cobble together my little equations. My mathematical abilities are very meager, to say the least. And SymPy would just produce this gorgeous, rendering that just kind of blew me away. Like I felt like I was looking at what my math teacher might have laid out in a test. And for it to be able to just sort of do that dynamically on the fly, I guess I knew that Unicode, in an abstract way, that Unicode had some shape rendering capabilities, but to see them used this way is totally awesome.
Yeah, that's actually it blew me away the first time I used it too. I especially when you look at most other computer algebra systems, if you use their terminal interface, their printing system is sort of rudimentary at best. You'll see things that like only use ASCII symbols, for example, which SymPy has as well. There's a version that only uses ASCII if you're in a limited environment that doesn't support Unicode. But I think the Unicode printing really makes a difference, because you can draw these large two-dimensional parentheses or whatever, and they actually look nice because they're connected.
Yeah, my experience with using Mathematica when I was in school definitely left a lot to be desired in the representation of the formulas that I was working with, and occasionally actually led to some confusion as to what it was actually trying to show me. And so having the visual characteristics of something like SymPy would have been very beneficial in those contexts.
Yeah, definitely.
So what are some of the challenges in creating documentation for a project like SymPy that is accessible to non-experts while still having the necessary information for professionals in the fields of mathematics?
Well, so our docs basically, we basically say in our docs that we're going to assume that you already know the mathematics behind whatever our docs are talking about, beyond just basic definitions. So, for example, if you read the SymPy tutorial in the introduction, it says that the tutorial assumes that the reader has a knowledge of basic introductory calculus. Basically, we don't have the resources to try to document the mathematics and the SymPy itself. And there are plenty of great resources out there to learn the mathematics. For example, there's Wikipedia, there's MathWorld, there's the Wolfram Function site. These are all great resources. And so I imagine this can be difficult for newcomers. There's actually a book that I reviewed recently on my blog called Doing Math with Python, which uses SymPy. And it takes an approach where it's only using like high school level mathematics. And it serves as a decent introduction to SymPy, as well as other mathematical aspects of Python. So if somebody actually doesn't necessarily know the calculus or the whatever the advanced math, that might be a more gentle introduction to SymPy.
And which fields of academia and business seem to be most heavily represented in the users of SymPy?
So as far as academia, there seems to be a pretty good following from physicists. Andre, the initial creator of SymPy, is a physicist. A lot of contributors have been physicists. I guess physics requires enough complicated math that it's nice to have something like SymPy to do some calculations. But aside from that, I see a lot of people use it to do what's known as code generation, which means that they'll use SymPy to generate the equations for whatever it is they're trying to model. And then SymPy has the ability to take those equations and generate C code or Fortran code that computes those equations. And so that's a lot nicer than writing out the C code by hand, because you might have a large amount, like a really huge equation that you don't want to try to write it out by hand. It's much better to have SymPy compute it for you, and you can do things like compute symbolic derivatives inside of SymPy and then generate code for that. This is actually part of what I'm working on as my day job. is improving this code generation stuff that's in SymPy. As far as business, there's less use in business compared to your standard data science or scientific libraries. But I have heard of it being used in here and there in like say the finance sector.
Yeah, I imagine that the code generation capabilities would be pretty difficult to create appropriate unit or integration tests, so I imagine that must be something that you spend a fair amount of time on to make sure that the code that it generates is correct and provably correct based on the inputs.
Yeah, well, so we do have tests that basically, if you run the tests, that they're not gonna run unless you have a compiler on your system. So we do have some tests for them, and also it's written in a modular way, so we can test most of it without actually compiling the code, just by testing that the code is whatever the code is generated. But yeah, I mean that is probably one of the more challenging things as far as testing in SymPy.
So what are some of the uses of SymPy in education outside of the obvious, like students checking their homework?
There are teachers who use SymPy to help them teach their class. I've noticed that it's actually pretty common, especially outside of the U.S., for instructors to use open source software in their class. And SymPy is a pretty common thing that I'll hear of teachers trying to use because it's a really nice open source computer algebra system.
So how does SymPy integrate with the Jupyter Notebook?
So as I mentioned earlier, if you can set it up so that your expressions will all automatically display as fancy printing. And the way that you do that is you import init printing, so that's init_printing from SymPy, and then you just call that function at the top of your notebook. And actually you call that function in any environment, not just in the notebook. And what that's going to do is that's going to set up the pretty printing for the whatever the best printing is possible in the environment that you're in. So in the notebook, that's going to set up the Mathjax printing, and in the terminal, that's going to set up the Unicode printing. If you're using the IPython Qt console, that's going to set it up so that it can actually call out to the LaTeX program if you have LaTeX installed, and generate math that way.
And is that leveraging the import hooks that are part of the Python language?
No. So as far as Jupyter goes, Jupyter has a whole printing system set up where different objects can sort of register different ways to display themselves. So a SymPy object can register itself as saying, I know how to display myself as math. And then the Jupyter Notebook knows that it can render math using Mathjax. And so it'll print that using Mathjax. And then the same thing similar in the Qt console, it displays the LaTeX math as an image.
And is SymPy generally used more as an interactive mathematics environment, or as a library that's integrated within a larger application?
So I both. Is actually one of the nice advantages of SymPy is that it is usable as a library. A lot of the other computer algebra systems are not necessarily designed with that in mind, and so it can be difficult to integrate them with other things. But since SymPy is basically just a Python library, it's really easy to just import it in your other library code. And we also try to make it so that SymPy objects are extensible. So for example, you can take one of the SymPy functions and subclass it if you want to change its behavior in some way. But on the other hand, yes, we also try to make it easy to use it as a calculator, basically. And that init printing in the Jupyter Notebook is a big part of that, because that makes it so that you have this nice printing. There's also another one called init session, and that's basically just going to also run a SymPy from SymPy endpoint star for you. So it kind of acts more like a traditional computer algebra system where all of the names are sort of there for you already. It's also going to define some symbol names for you, because in a traditional computer algebra system, if you just sort of type a variable name that isn't defined, it's just going to use that as a symbol. And since SymPy is in Python, we're not really hooking into, we're not really breaking the language. So undefined variables are still undefined. You have to define symbols. So you have to write x equals symbol x if you want to define x to be a symbol.
What were the challenges moving SymPy from Python 2 to Python 3?
I'd say that the worst thing there was that when we did it, 2 to 3 was still the recommended way of doing the transition. So that's how we ended up doing it, was with 2 to 3. And that ended up kind of being a mess because, if you wanted to run the tests in Python 3, you'd have to run 2 to 3 on the code base. And it basically, the workflow makes it so that you sort of just are still working in Python 2. And it's not really possible to work in Python 3 because that's sort of just generated code. And the 2 to 3 script takes a few minutes to run if it hasn't been run yet. And it's a pain. But then we eventually moved to a single code base, which is what pretty much everyone is doing these days. And I'm glad that the Python core team has changed their recommendation to doing that, because that's much better. That actually lets you use Python 3 as your active development environment. And there's no compilation step or anything like that to sort of compile your code from one language to another. It's just a single code base. And the two languages are similar enough. Well, they're not really two languages, they're one language, but the two versions of the language are similar enough that it's actually very simple to use a single code base for both. There's really, you just have to set up a compatibility file with some things that you have to import when you use them, and it's really not that big of a deal. It is a little bit challenging because we still support Python 2.6, which doesn't have a lot of the features. We also support Python 3.2, which doesn't have the Unicode literals. But I believe we used to support 2.5, which it was a lot harder to do a single code base with because it didn't even have the from future import print function. But if you're not supporting that anymore, which you shouldn't be, you shouldn't even be supporting 2.6 anymore, really, then there's no reason to not do a single code base.
It's tough because I think it's very easy for either of us to say you shouldn't be supporting 2.6 anymore, but there are a lot of people out there with environments where they may be moving to 3 or even 2.7 for their sort of future deployments, but they already have fleets of servers out there in the wild that are kind of locked into maintenance mode, where installing a whole new Python version just isn't practical.
I believe, was it Brett Cannon, one of the core developers, has basically come out and said that you should stop supporting Python 2.6 for free as a library developer. And so I think SymPy is going to drop support after the next version.
Sure.
And it shouldn't be very difficult to upgrade from 2.6 to 2.7 because there aren't any backwards and compatible changes, unlike updating Python 2 to 3, which can be a lot more difficult.
And to your point also, I think that, even when you are in situations like my situation at work actually is that we have 2.6 out there, but it's not clear how much development we're going to be doing on those servers. And if major new development ever is required, I, as a developer, am going to exert some upward pressure on my management to say, hey, we really got to upgrade the platform. You can't live in the past like this. Otherwise we're going to be sort of, working in legacy versions of everything and not being able to import anything new, and that's just not productive. So I think it's actually a tricky balance to strike, and I do totally understand that at some point you just have to cut the cord and say, okay, we're not doing it. It's 2.7 or bust. I think that makes a lot of sense.
Well, there's a lot of other libraries that aren't supporting it anymore, and I believe Python, the core Python, is no longer supporting it for security releases, that alone should be a reason for you to upgrade.
Yeah, that generally provides some decent impetus when the security releases are no longer available for a language or platform. That's generally when people finally start kicking it into gear and actually migrating upwards. I'm wondering if there are any features of Python 3 that you would like to be able to use but can't because of the fact that you're supporting both Python 2 and Python 3.
Oh yeah. Well, I mean, there's actually most of it's the stuff that I can't even use because we still have to support 2.6. Like we can't use dictionary comprehensions or set comprehensions or any of that stuff. So I'm, ever since I've been working on SymPy, we've had to support, several versions older than the latest version. So I'm sort of used to sort of not being able to use the newest features of Python until many years after they get introduced into the language. As far as Python 3 itself, I'm trying to think. I haven't really thought about what sorts of things we could do if we could support Python 3 only. I guess we could do some cool stuff with function annotations. What are the other cool features in Python 3?
They just recently released the matrix multiplication operator.
Actually, I don't know if we've added that to SymPy. SymPy does have symbolic matrices. I mean, we can add that can be added to SymPy. It's just you just have to define the matmul function on matrix. I should check if that's been implemented or not. And so anybody who's using 3.5 will be able to use that. Actually, 3.5 has some cool new features relating to star unpacking, where you can basically use the star operator to unpack things almost anywhere. So you can write stuff that's very sort of a lot terser than it would be otherwise, because you can do like two different star unpackings in the same function call, or you can write like an open square bracket and then a star and then a variable name and then a closed square bracket, and that'll create a list out of whatever that variable was. But yeah, it's not. I can use those in my personal projects, but it's going to be many years before, probably at least 2020, when CPython stops supporting Python 2.7, when SymPy is not going to be supporting Python 2 anymore.
Yeah, that will be an interesting year to see how many people run around with their hair on fire because they finally realize that they have to upgrade or they won't be able to get any more security updates on the Python 2 branch at all.
With that being said, I do want to highly recommend anybody who is looking into SymPy to use Python 3. One of the big feature or changes in Python 3 that you don't hear about much these days is the change of the division operator to do floating point division instead of integer division. So, for example, if you do 1 divided by 2 in Python 2, that's going to give you 0. In Python 3, it's going to give you 0.5. And that tends to catch people a lot who are, say, new to SymPy, because they'll try doing something like x to the 1/2 power, and they'll just write that out. And then x will just sort of disappear because that ends up just being x to the 0. That just turns into a 1. Or they'll like try to add 1/2 to an expression and it just goes away. And so, this is sort of one of the gotchas with SymPy, is that you have to sort of, if you want to divide two integers, you have to sort of wrap that around with SymPy types so that you get a rational number. So you have to write like rational 1, 2 to get the rational number 1/2. But if you're using Python 3, or if you import division from future import division in Python 2, you'll at least get a floating point number instead of what's basically the wrong answer that sort of just makes things disappear without you noticing, which is what happens in Python 2.
Yeah, that is definitely a tricky bug to find when you run into it, and I actually was having a similar situation when I was doing division between two integer numbers in SQL and wondering why I wasn't getting the expected results, and then remembering that I had to explicitly cast one of the operands to a float to be able to actually get a floating point result. So yes, definitely anytime you are wondering why it doesn't work and you're doing any division, then double check that.
I think anybody who's doing any kind of greenfield development these days, I think most people know you should just be using Python 3. There's really no reason not to. The sort of the old excuses of, well, this or that module isn't supported, it's kind of gone away, because those few modules that really just haven't been updated have been replaced pretty much. Other, honestly better, more modern modules that do exactly the same thing. And the few sort of really big, outliers like Twisted and a couple of others, even they are well on their way, and most of the important parts already work with Python 3. So there's just no reason not to at this point.
Yeah, I mean, I get it when you've got a legacy code base to work with, and you don't want to deal with porting it. But if you're say a new user to Python, there's no reason to not start with Python 3. And I'd say the thing that irks me the most is when I see people writing guides for new users or teaching courses for new users that are based on Python 2, because it's much better to learn Python 3 and then if that person needs to go and work with Python 2, then they can go learn how Python 2 is different from Python 3.
I'd be really kind of shocked to see any such new guides being written that point to Python 2. I mean, I think once Django updated all their sort of getting started documentation to Python 3, I think a lot of other people fell in at that point.
Yeah, it's definitely fewer and fewer these days, but you'll still see them if you're, or even just like maybe not a guide to Python, but just like a tutorial of something that's using Python, and the author happens to use Python too.
So were there any performance bottlenecks you needed to overcome in creating SymPy?
Unfortunately, Andre couldn't make it, but yeah, the performance is a problem because, like I said earlier, it's really easy to sort of create an expression that's arbitrarily complex. So, for example, one of the functions in SymPy is factor, and what that does is it takes a polynomial and factors it into the products of irreducible polynomials. So, for example, if you do factor x squared minus 1, that'll spit out x plus 1 times x minus 1. And so if you sort of look at the runtime complexity of factor, it's based on the degree of the polynomial. So if I have x squared minus 1 is a second degree polynomial, but it's really easy to create a million degree polynomial without and it's not very large when you type it out, because you're just typing x to the 1 million. So that's about I guess that's about 10 characters right there. And then so it's really easy to create some million degree polynomial that's going to take forever to factor, because the complexity of it has to do with the degree of the polynomial. And so that's just a simple example to show that in a lot of the cases, the sort of the algorithmic complexity of a function might not have to do with the actual size of the input, but maybe one of the numbers that appears in the input. And so another issue is that it's very easy to sort of write a symbolic algorithm in a naive way that ends up being extremely inefficient, like maybe exponentially slow when it can actually be maybe run in like linear time or something like that. So for example, if you just sort of naively try to write an algorithm to expand the product of two polynomials, I guess a better example would be to expand the power of a polynomial. So say x plus 1 to the third power. If you sort of try to write that out naively, what it is, you get something that's very inefficient. But the correct algorithm sort of requires knowing what how these multinomial coefficients work and something like that. So it's pretty common. It's not uncommon for somebody to put an algorithm in SymPy that ends up being inefficient just because it's not as algorithmically well designed as it could be. And I guess the other final problem is that Python as a language can be slow, and it's difficult. It's not really a lot of the things that sort of make it faster don't really work very well for SymPy. So, for example, if you try running SymPy through PyPy, it can actually end up being slower than just CPython, because a lot of the dynamic stuff that SymPy is doing sort of doesn't really work with PyPy's jitting. And a lot of these other things like Numba, for example, they're not going to work at all with SymPy, because those are designed around numerical algorithms and not this object-oriented stuff that SymPy is using. And so there's a lot of dynamics. SymPy takes huge advantage of the dynamic nature of Python, and it can be slow. Andrei Surtek is actually working on a project called SymEngine, which is maybe not a rewrite, but it's a new core of a symbolic engine written in C++. We'll eventually be able to sort of swap out the core of SymPy with SymEngine so that the fundamental operations inside of SymPy can be faster.
Interesting. It definitely sounds like one of those problem domains where it's like one step, two step, okay, it's reasonably shallow, it's all good. And then the third step, it's like, whoa, it's like a bottomless chasm. It sounds like its difficulty of one expression to another can be very, very uneven computationally speaking.
Oh, absolutely. Because, you're basically trying to compute on all of mathematics. So if you think of the hardest math that you had to do in high school or college, it's SymPy is trying to do stuff like that.
So forgive me if you've already answered most of this in the previous question, but perhaps not, so I'm going to ask it anyway. What are some of the interesting design or implementation challenges you've found when creating and maintaining SymPy?
I would say that it's difficult to, or interesting even, just how you design the core system of SymPy. Once you sort of have the basic symbolics, like I can create some symbolic expression, and I have some ways of manipulating it. Once you have that, sort of doing these higher algorithms on, like, here's how I solve functions or equality, or here's how I simplify an expression. Those tend to be easier, but the actual getting down to how do you actually design it so that what does the type system look like? What are the ways that you manipulate an expression? And there are several different approaches to doing that. And a SymPy expression is basically a tree. So if you think of something like x squared plus 1, that would be so the top level expression of that is an addition. So that might be represented as add x squared and 1. And then the x squared is the power, so that would be like pow x2. And so you have this tree where the nodes are these, the leaf nodes are these like usually symbols or numbers, and then the higher nodes are the functions that contain those. And so most symbolic algorithms end up being sort of these tree manipulation algorithms. And there's different approaches to doing tree manipulation algorithms.
And are there any new features or major updates to SymPy that you have planned? I know you mentioned the SymEngine, but I'm wondering if there's anything else.
So SymEngine is a separate project from SymPy. We do have a release planned, hopefully pretty soon. It's actually going to be a 1.0 release, because we've been releasing versions that are less than 1.0 for too long, and it's time to. SymPy is a full-featured computer algebra system at this point, and it's time for our version numbers to reflect that. As far as the new changes in this release, most of them are going to be coming from our Google Summer of Code projects from this past summer, and I don't want to. I'm sure I'm going to leave some stuff out because we had several of them, but just to highlight some of the ones that I remember. The solvers module, which is basically the module that deals with solving equations. So solving x squared minus 1 equals 0. The solutions there are plus or minus 1. So that the solvers module is sort of being rewritten to use sets. So one of the issues with the current solvers module is that it sort of returns just this list of solutions. But it's not the problem with just a Python list of solutions is you can't really represent things like infinitely many solutions with that, and it's also not really a mathematical object. And so SymPy has the sets module, which lets you represent mathematical sets. So, for example, there's an object that represents the set of integers, and there's another object that represents the set of real numbers, and you can do things like unions and complements and stuff like that. And so the new solve set module will return a set when you solve. And so that lets you do things like, say, solve sine x equals 0 the solution to that is n times pi, where n is an integer. So that's an infinite number of solutions. And so that this can actually represent that as sort of a set, the set n times pi, where n is an integer. And so this lets us represent a lot more possible solutions. And the other nice thing about the solve set module is that it actually it's able to sort of give you some guarantees about whether or not it's found all the solutions. So one of the issues with SymPy's current solve module is that you can't, if you pass it a function and it returns, say, an empty list, there's no way to know that that just means that there's no solutions, or that means that SymPy wasn't able to find any solutions, which is, that can be problematic. So, for example, if you want to write a little function that finds the maximas and minimas of a function, so from calculus we know that we can just take the derivative and solve where it equals 0. But the problem is if you need to know everywhere where it equals 0, otherwise you might miss one of the maximal points, and it might not actually, the one that you find might not actually be the global maximum. And so the solve set module makes it easier to implement stuff like that. Another thing that's continuously improving, and there are going to be a lot of improvements in the next version, is our assumption system, which the assumption system deals with making assumptions on expressions. So, for example, I want to say I have a symbol x and I want to assume that it's positive. And this is important because there are a lot of sort of mathematical operations which are only valid under certain conditions. So a classic example is if you take the square root of x squared, that's x squared and then the square root of that. That expression is only equal to x if x is positive. So, for example, if x is not positive, if x is negative, then it doesn't equal x, it equals negative x. And so if you want to simplify that, the square root of x squared down to x, you're going to have to assume somewhere that x is positive. And so our assumption system lets you do that. And there's a lot of other examples throughout SymPy where it needs to check some assumptions on some expression in order to perform an operation because it's only valid for that domain. And so the SymPy assumption system has sort of a colored history. There's an old system and a new system. I don't want to get into too many details because that's going to be a lot longer than what I want to say. But we're working on sort of replacing the old system with the new system.
And how is the evolution of SymPy managed from a feature perspective? And have there been any occasions in recent memory where a pull request had to be rejected because it didn't fit with the vision for the project?
So that the actual things that fit into SymPy is very broad. Basically, anything that can sort of be mathematically, symbolically represented is a good fit for SymPy. So if you look at if you go to GitHub, github.com/SymPy/SymPy, and you look in the SymPy module at all the submodules, you can see there's a huge range of modules. There's a logic module, there's matrices, there's number theory, there's physics. But as far as things that actually don't fit, anything that's sort of not a symbolic thing. So, for example, numeric stuff, we try to leave that to other libraries which do that much better, like SciPy or NumPy. And another example would be graph theory. There are plenty of good graph theory modules. So yeah, I would say that most things that don't actually make it to pull requests that would be rejected. So I don't have any examples of pull requests, but we do get a lot of people who want to implement stuff that are basically not symbolic. So they're not. It's not that they're bad ideas, but they are better fit for other libraries. And the great thing about Python is that it's easy to sort of use SymPy and these other libraries together. So it's not really necessary for them to go into SymPy for them to be usable by users of SymPy.
And which of the features of SymPy do you find yourself using most often?
Well, so back when I was in college, I used it to help me do my homework, which, I guess that varied depending on what specific class I was in. I majored in mathematics, so I took a lot of different mathematics classes. These days, I use it. I do development in it, but as far as just using it, I mainly use it as just a calculator. If I see something interesting online about mathematics, I'll plug it in there. I like to peruse, I guess it's Math Stack Exchange, and sort of look at some of the questions there. And sometimes I'll plug stuff in there. Or if I see something cool online that I wonder if SymPy can do that. Then I like recently I apparently if on Twitter, if you use the poll feature, where you can create a poll where people can vote on things, you can actually squeeze more than 140 characters into there. And so I figured out the new character limit was like, I think 157. If you include like the poll answers. And so there's this question of, what's the largest prime number that can fit in the tweet? And it's really easy to compute that with SymPy because there's just a function called prev prime, and you just do prev prime 10 to the 140, and that'll give you the largest 140 character prime in base 10. And so I recently computed the largest 157 or whatever it was character prime and tweeted that out as a poll. Somebody voted on one of the poll responses, which was just a bunch of 9s.
So before we move to the Pics, is there anything that we didn't ask that you think we should have, or anything else that you'd like to bring up?
I guess I would mention that we are very welcoming to new contributors for SymPy. So if you're interested in this sort of stuff and you may be new to open source, come check us out. We have if you go to our website, it'll point you to where to go. But we have a Gitter channel where you can go to get started, and there's some pages on our wiki on how to get started with SymPy development. And we have some issues in our issue tracker that are tagged as easier to fix issues for people who are new. And yeah, we try to be as welcoming as possible to new contributors, because that's ultimately how most SymPy developers sort of started out.
Great. So with that, I will move us to the Pics. And my first pick this week is going to be the podcast Functional Geekery. It's one that I've been listening to for a little while, and the host has on people from various languages in the functional space. So they'll, one week he might have somebody talking about their work in Erlang, and the next week it might be somebody talking about Clojure, and then followed by somebody talking about Haskell. So it's just an interesting way to learn more about functional programming and some of the work that people are doing on that side of the fence. So been appreciating that. My next pick is a music pick that I stumbled across while I was listening to Spotify. It's called Necrogoblicon. It's melodic death metal, and it's actually pretty enjoyable. I've been listening to that a bit lately, and in particular their latest album called Heavy Meta. So for anybody who listens to metal at all, definitely worth at least trying it out. And my last pick this week is going to be Marble Fun Run. So, if you've ever seen the marble tracks that you can snap together in various ways and has different shaped bits. So, some of them are curvy, some of them have little water wheels that'll spin as the marbles go down. I recently picked up a set of those for my kids. Just a good way to pass the time and experiment with different flows of the marbles. And with that, I will pass it to you, Chris.
Cool beans. My first pick is a new podcast called Surprisingly Awesome. And each week they showcase something that seems kind of mundane, but that it actually has some really interesting characteristics about it. Like one week recently they showcased Tub Thumping by Chumbawamba, which for any of us who were around during that time period, just got overplayed to death. But did you realize that they were actually a, hard-edged punk anarcho collective before they became a pop band? So it's that kind of thing. It's very fun. My next pick is a documentary that Avdi Grimm had recommended, and I sort of, really I'm a huge fan of his and follow most of what he writes about. So I thought, I should give this a shot. And I have to say, it's really interesting. I'm not sure I entirely agree with everything that the author has to say, but it's incredibly thought-provoking and visually beautiful with all sorts of really great footage. It's called All Washed Over by Machines of Loving Grace. It's an old documentary, 2011, from the BBC, and the basic premise that the author makes is at the dawn of the computing era, people had, some of the pioneers in the industry had thought that with computing power on the increase, we would be able to create this sort of worldwide utopia, and we'd be able to do away with government, and that just hasn't panned out. And he has some really interesting interviews showing footage of like Ayn Rand, and it's really interesting, thought-provoking stuff. I could go on and on about it, but I won't. I think you should watch it and let me know what you think. My next pick is a Japanese pop band, because I watched that documentary and the theme song from it stuck in my head and just burned its way into my brain. And I said, I gotta hunt this down and figure out who these folks are. It is a Japanese pop band called Pizzicato 5. And as I said, the theme song for that documentary is made by them, called Baby Love Child. It's just a really interesting kind of quirky Japanese pop sound. I really like it. My last pick is a beer. I encountered this last night, actually. It's called Mayflower Hoppy Brown Ale. I've also seen it as their Cooper series brown ale. It's really kind of interesting because most of the time when you see brown ales, they're very sort of malty and don't have much of a hop signature. But this one has some really sort of pronounced hops. And so it's really kind of an interesting, neither fish nor fowl. It's neither a brown ale kind of, or I should say, it's not like the average brown ale and it's so hoppy. It's also not an IPA because it does have the usual sort of, malts you find in a brown ale. It's really tasty stuff and something a little unusual to tickle your palate if you're a beer fan and in need of a change. Aaron, what picks do you have for us?
Yeah, so I don't have nearly as many as you guys do, but I guess so. My first pick is going to be a website called Vermonts Library, and this is for anybody who is interested in mathematics, or I guess there's also some physics here. So the idea of this is that they pick a paper each week and present it in this way that where you can people can comment on it in the margins, sort of like how Vermont famously did with his theorem that he never actually proved. And so there's some interesting papers here. I think this is just a great way to sort of see an interesting paper every once in a while, and they tend to be very short papers as well. There's one here is the Bitcoin paper by Satoshi Nakamoto. There's a paper here on a simple proof that pi is irrational. There's a paper here that's the shortest. What was it? The shortest paper ever published in a serious math journal by John Conway and Alexander Soiferi. You should look at what that is. And so if you're interested in mathematics as I am, I think that's a great thing. My next pick, I don't know how self-promotional these picks are allowed to be, but
as much as you want.
As much as you want, go for it.
This is actually, it doesn't. This is just a little thing that I wrote that I was reminded of today, which is called cat image. So I guess this is sort of two picks. One is if you use OS 10 and use a terminal at all, I highly recommend that you use iTerm2 instead of the default terminal that comes with OS 10, because it is just amazing, and it has just a huge amount of features. It's easily the best terminal emulator on any operating system. And so one of the features is that you can actually display images in the terminal by doing some special escape sequences. And so what I've done is I created a little program that goes to Imgur and downloads an image of a cat and displays it in your terminal. And so this is I have this at the top of my bash profile where you just type cat image, that's CATIMG, and it'll download a cat from Imgur and display it in your terminal. And so I at the top of my bash profile, I have a cat image, and then it displays a fortune from the fortune program. And so whenever I open a new terminal tab, I'm greeted with a nice cat. You can install that with pip install cat image or conda install cat image from my conda channel.
So for anybody who wants to follow what you're up to and keep in touch with you, what would be the best way for them to do that?
Well, for me specifically, probably the best way would be my Twitter, which is ASMeurer. It's ASMEURER. I'm fairly active on Twitter, so now for SymPy, I would recommend the SymPy mailing list and Gitter channel. And if you Google either of those, you should find those quite easily.
All right. Well, we appreciate you taking the time to join us this evening, and I definitely enjoyed learning some more about SymPy and computer algebra systems in general.
Very cool. Thank you very much for taking the time to talk to us. SymPy is a really neat project, and I've only sort of scratched the surface with it. Mathematics is one of those things that I feel like I'm just at the sort of very outlying edge of my own capabilities with it, and SymPy seems like a really great exploration tool to sort of broaden my mathematical horizons. Thank you.
Well, you shouldn't feel bad, because there are areas in SymPy where I have no idea what's going on because I don't know the mathematics behind it. So I don't know if there's any one person who actually is capable of understanding everything in there.
And if they do, they should step forward.
All right. Well, thank you for having me.
Good night.
Have a good night.
Good night.